Hey everyone, we are Group F, the cell phone forearm holder, and I am Sin.
And I'm Emily.
And I'm Jacob, and our motivation for this project is that we saw a niche in the market for a cell phone carrier that is hands-free. And we wanted the carrier to be on the forearm, and we wanted the phone to be usable in several different positions and orientations.
So we ran a quick poll asking people what they wanted from such a device. It became clear that what was important was for the phone to be very secure on the forearm and for it to be used with one hand and have an easy removal from the apparatus.
And as for our problem statement, cell phones are a continuously evolving technology and an integral part of modern life. Just about everything can be done with cell phones. However, as technology changes and cell phones evolve, there is always been one constant. Cell phones are always handheld. Our problem is to design an integrated system that conceals cell phones while traveling and provides an easy access apparatus for cell phone use on the forearm.
There are a few standards that are relevant to our design. This is a unique project in that it has potential to be a fashion statement as much as a tool. Therefore, we designed it to the military standard 810G. This standard includes codes for drop tests and waterproof tests, as well as tests that are not relevant to the market for our product. We did our best to design to this standard, but because we are facing significant manufacturing constraints, it was difficult to meet the standard. Furthermore, WashU doesn't have the facilities we would need to test the standard. Our first preliminary design was a solid shell with an L-shaped track. It had a spherical carriage that slides through a cylindrical track with a peg and disc attachment that extends out of the track. There were 6 convex dimples on the disc. There's a U-shaped envelope on the phone case that the disc slides into. On the interior of the envelope, there are 6 concave dimples that match the ones on the disc, so the phone can rotate and lock into place. Our second preliminary design was also a solid shell, with a hooked helical track with a circular cross-section. The spherical carriage slides in and out of the track, and the phone attaches to the carriage, similarly to the first design. Our third preliminary design, again, had a spherical carriage, but this time it had a longer arm extending from the carriage to the phone. Straight spherical track is partially closed on one end to create a partial ball joint so the phone can extend to be used in the hand while remaining attached to the track. All these designs were close, but after some further designing, we decided to create a helical track with a carriage that had wheels and axles. After even more experimentation and design revision, we ended up with a helical track with a carriage that has a keyhole instead of wheels to slide along the track.
Some possible prototype upgrades would be to increase the security of the connection to the forearm. One way would be to include a thicker base on the track with slats cutting through that would allow for straps to be threaded through the slats to connect more securely to the forearm, or the possibility for sewing the track onto a compression sleeve. Another possible upgrade for the prototype would be taller end caps so that the carriage is easier to keep at each end. One more possible upgrade would be a customizable carriage size for different phone dimensions. The performance goals of our project were to have a carriage where the phone would slide along the track from one end to the other. The carriage would stay at either end indefinitely for storage when not in use, and the phone could be oriented any way the user would prefer for ease of use and ergonomic preference, to have easily replaceable parts in case of failure or breaking, and that the apparatus would be convenient to wear over long sleeves or on bare arms.
As for our engineering analysis, we performed 3 static tests and 1 dynamic test. For our first static test, a load was applied to the track. The ends of the track were held as fixed points, and gravity was added in the negative z direction. There was a 1.12 pound force applied along the track. Our second test was a load applied to the carriage. The keyhole area was held as a fixed point, gravity was added in the negative z direction, and a 0.3 pound force was applied to the top of the carriage. Our third test was a torque applied to the carriage. The top of the carriage was held as a fixed point, gravity was added in the negative z direction, and a 0.2 pound force torque was applied to the keyhole. Our motion study is still in progress. We've experienced a lot of difficulties with SolidWorks simulation because the tolerances we needed for the keyhole to slide smoothly along the track made it very difficult to mate the keyhole and the track. But our motion study will show how end caps fit into the track, how the carriage is removable, and that the carriage can move along the full length of the track.
Now onto our results. Specifically, all of the stress tests that we did on our parts were von Mises stresses. A little bit of background. The blue color means there's virtually no to very little stress. Green means that there's moderate stress, and red means there is the maximum stress. We computed our results under standard operating conditions. This means that our part was under normal gravity and pressure. There was an average sized phone, not any sort of tablet or other device, and that all of the parts were undamaged and were properly made. The part that you see now is the track that has a load applied to it. As you can see, the area is mostly green and blue since there are no big forces affecting the track. The only place that we have to worry about is the orange and red that shows on the bottom exterior of the track. This is due to the shape, which is a helix, and the particular forces that we've put on the track. This next piece is the load applied to the carriage. Again, the piece is mostly green and blue since there are no big forces affecting the track. There are two main areas that show orange and red. The first one is along the filleted side near the bending, while the second one is actually along the bending on the top part of the carriage. It should be noted that all of these bendings are highly exaggerated in order to be seen, otherwise they'd be on the very small order of magnitudes. This next piece shows the torque that's being applied to the carriage. Finally, as was mentioned earlier, our motion study is still in progress. The only reason that the motion study is going to be done is to be a proof of concept in the virtual world. Now we want to talk about the risks and design constraints of our project. For our project, we had three main risks, the first one being printing error. 3D printers are still reasonably new technology, and as forth, they're very limited when dealing with small components like our project is. The second risk was ordering parts. As always, you have to take into account shipping times and any sort of delays that could happen, and you also have to take into account any defective parts and reordering that would have to be done. The final risk is the actual strength of the plastic. As for our design constraints for our project, there is one main constraint that affected the entire project, and this is universality. In other words, everyone is a little bit different, so we had to try to take into account that everyone's forearm and wrist dimensions would be ever slightly different.
All the parts for this project were 3D printed in-house here at Washington University. Our in-house printing was free for engineering students, so that doesn't give us a very good idea of the budget required for this prototype. So after looking up some data, even if we had to pay for the plastics used in the printing process, our budget would still be very low, because ABS plastic for 3D printers is very cheap, ranging from less than 2 cents a gram to about 18 cents a gram. And if we had to print somewhere that does print jobs, where we wouldn't pay for the plastic, but we would pay for the service of having it printed, by order it would cost roughly between 15 cents a gram and 25 cents a gram, which still leaves us with a very small budget.
Now we want to take a moment and talk about integrating other elements of engineering into our project. Without leaving the scope of our project, we came up with the idea of creating an algorithm for mass production. In other words, an individual would be able to input their forearm and wrist dimensions as well as the dimensions of their phone into a program. This program would then automatically adjust a CAD model. This programming would be an example of integrating computer engineering into our project.
This project has several next steps and out-of-scope suggestions that we would like to implement as our project moves past the prototype stage and towards manufacturing. Some of these suggestions and steps include motorization, where at the push of a button, the cell phone would change positions on the track along the forearm, or at the push of a different button, the cell phone would be able to change its orientation about where it's at on the track for ease of use and one-handed use. Some other steps and suggestions would be injection molding instead of 3D printing for the track, because the printers did not like building the support structure for the track, and it would be much cleaner and more precise to do injection molding. We would also like to return to the original design of the cell phone holder and carriage, where it had the dimples that allowed for locking into certain orientations that we had to abandon because of our limitations of manufacturing.